Okay, we have all this wonderful data about the maser. How can we use it to actually measure its distance? Well, let's take stock of what we actually know. We're on the Earth over here, and in the middle of the maser we have a black hole, which I will draw in blue so it shows up, of unknown mass m. And we can see a whole bunch of blobs orbiting it. Let's for the moment just consider one blob out here to the side and one blob in front. Now what can we measure? Well, we can measure the velocity of this blob out of here using the Doppler effect, so we'll call that v1. We can't measure the distance from the black hole, but we can measure the angle. So let's draw an imaginary line along here and one up there, and we can measure that angle theta. What we want, of course, is the total distance here. How about this blob in the front there? What we know about that is its acceleration. We look at how much its velocity is changing, which is going to be pointing towards the center, so we know some acceleration a. And we can also measure its angular speed sideways. So let's imagine that it's actually at an angle, a very small angle, phi in here, and what we can measure is the rate of change of phi dot. Two other things we don't know. We don't know this radius here, which I'm going to call R1, how far the sideways things are, and we don't know how far in front, which I call R2, the blobs that we see along the line of sight are. So we know v1, theta, acceleration a, and phi dot, and what we want to work out is d, the distance from the Earth to this maser. Okay, so let's start off with, let's call this blob 1 here, and we'll call this one blob 2. In reality, you do this calculation for many, many blobs on both sides, but the bare minimum you need is one blob to the side and one blob in front. So if you take blob 1, now we don't know R1, but we do know that that's equal to theta times the distance. So we know that R1 equals theta times the distance using the small angle approximation that we've used many times in the course. The other thing we know is we can balance centrifugal force against gravity. So we know that m of the blob, small m, v1 squared over r1 equals the gravitational force, g big M of the black hole, small m over r1 squared. So rearranging that, we find that the mass of the actual blob cancels out, one of the r1's cancel, and we can get an expression for the unknown mass of the black hole, which is that the mass of the black hole equals r1, which is theta d, times the velocity, which we know, squared over g. So the only thing in this equation we don't know is how far away the maser is from the Earth. Okay, so that's a good start, but not enough by itself. We've got two unknowns, d and m, in this equation. We're going to need another equation to solve it. So let's go for blob 2. Now in this case we know a bunch of stuff. We know the acceleration, and the acceleration, when anything's going in a circle, is this over here, mv squared over r. Well, that's actually the force, so the acceleration is divided by the mass. So the acceleration, which we can observe by looking at how much the Doppler shift changes, is going to be equal to the velocity of the second object. Let's call that v2. So v2 squared over r2, which doesn't really help us as we don't know either v2 or r2. Let's rearrange it to make r2 the subject, so r2 equals v2 squared over a. So what we'd like is another equation for r2, which we can use to cancel this out. And once again we can balance centrifugal force against gravity, which gives us that G big M small m over R2 squared equals small m V2 squared over R2, just as we did above. So if we rearrange that, we find that R2 equals G m over V2 squared. So now we've got two equations, this one and this one, both of which give us R2. So if we set them equal to each other, we can hopefully get rid of R2, which we don't really care about. So let's set those two equations equal to each other, and we get an expression for the acceleration. A equals V2 to the fourth over Gm. And now with R2 cancelled out, we arrange that to get m, and we get m equals V2. Now V2 is just phi dot times the distance. Small angle approximation again. So that's going to be phi dot d to the fourth over G A. So it's the second equation for the mass. We have the first equation up here. So what we can do is set them equal to each other. So we get that theta d v1 squared over g, that's what we got from blob 1, is equal to phi dot to the fourth d to the fourth over g times the acceleration. So the g's cancel, one of the d's cancels, and what we find is d equals the cube root theta v1 squared a all over phi dot to the fourth power. So we can work out d in terms of only things we can measure: theta, how far away the side dots are from the center, the Doppler velocity of those side dots, the acceleration of the object in front, and the angular speed of the object in front raised to the fourth power. In practice, of course, you have to worry about whether these dots are actually moving, the blobs are actually moving in perfect circles, whether the disk is actually warped. On the other hand, you typically have lots and lots of different blobs to use, so you can try and calculate these two different expressions over lots and lots of the different ones and try and fit them all simultaneously. So you can get some pretty good data here.